topic is something that you did not cover in the course yet, which means everything you know about this is only something you covered probably not even in high school, probably back in middle school. And I know for a fact you remember nothing from it, but probably you remember the essence. Like anything you know about Archimedes upthrust, can you please tell me? Or buoyancy, anything you remember, what it is. Can you please tell me? Anything you remember, I'm all ears. Yes. Buoyancy, Archimedes upthrust. Where does it happen? All right, so you're talking about fluids. And by fluids, I do understand liquids and gases. And that's why basically helium, which is a gas, the atmosphere, helium floats. You're talking about floating. Okay. And you're talking about its opposite to gravity, upward. I love the fact that you said upward. It's an upthrust, so opposing to gravity. It only occurs on solids. It doesn't have to be solids. It doesn't have to be water, Jana, but I love the word immersed. So immersed is a very interesting idea to discuss. So you should be immersed in the fluid to feel buoyancy. All right, so let me start by discussing a bit the setup before discussing all that again, the setup itself. And I'm gonna save as, because I don't wanna do the same mistake again, save as for your class so I can send you your actual PowerPoint. This is the setup. I will explain the setup and then ask you some more questions. What we have a stand, and by the way, you can build the stand. You will be given rods and you build it the height you want. And you can have a platform like a stand for your actual rods. Yes. And you have this sensor. I'm sorry for the double figure. Probably it was a mistake I did long time ago. So this sensor, what do you call it? What does it do? Can you guess? Yes. So my question is, the sensor, what does it do? Did you ever see this sensor before? Okay, so basically, let's say it measures the weight or the apparent weight. Or yes, Diana, the name is a force sensor. We already saw the force sensor in lab collision, which is lab 4. And we already said that the force sensor needs calibration. So I'm going to calibrate it for you. However, the force sensor in lab 4 was measuring the pushing force. It had a bumper in here and not a hook. And we were actually compressing it and not pulling it out. So now we're going to remove the bumper and put a hook with a wire, you know, and attach a cylinder to the wire. In other words, the force sensor can measure the weight or the apparent weight of the cylinder. Don't forget that after I do the calibration for the force sensor, you need to zero the force sensor, then put the wire and the cylinder to do the right measurement. Don't forget that you need to zero your force sensor. Now the question is, some students are saying that the force sensor is gonna measure the weight, and some students are saying it's gonna measure the apparent weight. So what's the difference between real weight and and apparent weight? And in which case the force sensor is giving me the real weight, and in which case it's giving me the apparent weight? And you can unmute yourself, it's okay. It's lovely to hear you.
The apparent weight is the weight that the object seems to have when it is in water.
All right.
Whereas the actual weight is its real weight outside of any fluids.
Okay, so to measure the real weight, we make sure that the cylinder is outside the liquid, and whatever measurement the force sensor is giving me is going to be the real weight. And if the cylinder is inside the liquid, it's going to be the apparent weight. Okay? Now, probably I need to go back to the Archimedes upthrust and probably discuss the fact that this is a container and I have a certain liquid and I have an object in here. Can you tell me what are the forces on my object or system? You can unmute yourself. It's okay. We are a small class. All right. So the first force is the weight. I'm going to draw the weight. I will call it mg. Any other force you think the object is subject to? It's funny when I said you're so active, I love it. Now everybody's not active anymore. Probably my questions are more difficult. So an object is immersed in a fluid, in a liquid, and the forces on the object are, why Naromi? You used to answer all the questions. Basically, the object is not moving. Probably there is friction if it's moving. Why not? I'm not gonna say no. What other than the weight and probably friction if it's moving? Something similar to the normal, and it's the force of the water on the object. What do you call it? It's the buoyant force. Yes, not the pressure, we call it the buoyant force. So we have an upward force. Yeah, it's an upthrust. It's the Archimedes upthrust. You can call it buoyant force or Archimedes upthrust. So we have F and mg. So yes, you can call it buoyant force or Archimedes upthrust. Now the question is, in which case the object is gonna sink and in which case the object is gonna float? How do we know? So if the weight is greater than the force, obviously the object is gonna sink, which means when objects are sinking in water, some students would think there's no Archimedes force on them, which is wrong. Archimedes upthrust is always on them. However, the weight could be greater than the force. So when mg is greater than the force, the object is gonna sink. And whenever the mg is smaller than the force, the object is gonna move up, and whenever it reaches the surface of the water, this is where F and mg are equal. This is where you have equilibrium, okay? So when F is greater than mg, you will end up with some motion until you reach equilibrium. Even with sinking, whenever the object is sinking, it means you will have some motion until it hits the bottom of the container. This is where equilibrium occurs due to the Archimedes upthrust, the mg, and the normal force, the normal reaction because of the bottom of the container holding the object up. Okay, so yeah, definitely. Now we know how to calculate the weight. It's m times g, or we can simply measure it by a force sensor outside water and call it the real weight. However, how do you calculate the force? What does it depend on? What do you do to increase the buoyancy? Any idea? What is it related to? The upthrust. It's due to what?
Is it related to the viscosity of the fluid?
So it is related to the density of the fluid, not the viscosity. All right. And yes, this is the fluid nature, but the nature, Romy, could be viscosity, could be density, could be probably opacity. You know, some are transparent. So density only. All right. Not viscosity. The viscosity will affect the motion and the speed. And here we're doing equilibrium problems. Equilibrium problems meaning no motion, meaning no friction, meaning no viscosity, no speed. I know for a fact that just before it starts sinking, like it's sinking, just before it reaches equilibrium, we have a tiny fraction of time where you have motion, but we're not studying this. We're only studying the part where the object is at equilibrium, so no viscosity. Volume, Rita and Christopher, what do you mean? Which volume? And what do you mean by volume immersed, Christopher? Yeah, so this is my object. Which is my immersed volume? Volume of the liquid. All right, so you take all the liquid, right? So if you have a small pool or a big pool, the Archimedes upthrust is gonna be different. All right, so somebody's saying it depends on G as well. I still have an issue with the volume. I need people to explain how the Archimedes upthrust is related to the volume. The volume of who? The volume submerged, Kausar, yes. And let me explain. So it's not the whole volume, Romy. It's only the immersed volume. And the immersed volume is only the part, so not the liquid. It has nothing to do with the volume of the liquid. It's only the immersed part of the solid, which means if you're standing in a very shallow pool and the water is up to your knees, you take only the volume of the legs up to the knees. You know what I mean? Yes, and it's proportional to the immersed volume. I'm gonna call it V immersed, okay? So yes, to find the Archimedes upthrust, it's related to the density of the liquid and not the object. A lot of students would think it is related to the density of the object, because if I have an object that is more dense, I'm gonna sink. It has nothing to do with that. Sinking or floating has nothing to do with F. F could be huge, and yet you can sink if your weight is even greater. It does have something to do with gravity, because eventually it's in newtons, and gravity, the force, all forces are affected by gravity, and it is related to V, because the more volume you occupy inside the liquid, you push the liquid away, and then Newton's third law, for every action there's an equal and opposite reaction, the liquid is gonna push you back. Now back to the questions, Roy. How can we know that exactly, like volume? I think the sensor helps in doing that. Good question. Now back to the experiment. All right, so what are we gonna do? We're gonna start by measuring the weight outside the water, and we're gonna call it the real weight, okay? And then we're gonna start dipping the cylinder bit by bit inside the liquid. How? We can do it using two methods. Either unscrew and lower the force sensor for the cylinder to be lowered inside the liquid, or simply I can raise the platform up by the depth I want. For example, raising the platform with a 0.5 centimeter would make my cylinder dip 0.5 centimeter inside the liquid. All right? So if you want, this is a table of measurements. I'm gonna take depth 0 to measure the real weight. So this is not buoyant force, it's the weight. So here I'm gonna do real weight, okay? And then I'm gonna take 5 millimeter depth. I will dip the cylinder only 5 millimeters, and I'm gonna find the apparent weight, because outside water it's called real weight, and inside water it's called apparent weight. And then dip the cylinder 5 extra millimeters, so I'm up to 10 millimeters, and find the new apparent weight again, and so on. All right, so the height is gonna be the difference. I'm sorry. Yes, so I'm gonna start dipping, that's my variable, the depth inside the water, and find the apparent weight. Question, if I have the real weight and the apparent weight, how do you find the Archimedes upthrust? That's question number 1. So I measure the real weight, I measure the apparent weight. Probably the real weight is 10 newtons. Yes, I minus them. And okay, let me write it as such. The real weight, that's an example, is equal to 10 newtons. Okay, the apparent weight is always less because of the upthrust making you feel lighter. Let's say this is 7.5 newtons. How do you find the upthrust? You say that the upthrust by definition is simply the difference. So 10 minus 7.5, this is how much the force is pushing you up. Yes, so the real weight minus the apparent weight. So far your force sensor is gonna measure the apparent weight for you, and you are gonna do the calculation to find the buoyant force for each trial, for each measurement, okay? Now I have another question. We already said that the buoyant force is rho, which is the density of the liquid. So let me write it again. I don't like to use rho. I think it makes it more difficult, sound difficult. So density of the liquid. I stress on L because a lot of students will think it's the density of the solid. G is the gravity, gravitational field strength, and Vm is the volume that is immersed under the liquid. Now, question. How do I find the Vm? How do I calculate the Vm? Or measure? It's up to you. You are in the lab, you are alone, and you are requested to measure V immersed. How do you do it? Give me any method, measure, calculate, anything you want. The morning section gave me 2 methods. So
we measure the volume of the water where nothing is immersed, and then we put the object and we measure how much the volume changes.
All right, this is called, we measure the displaced liquid. Like, for example, you have, for example, the level of water was initially here, and then it went up to here. So the difference in the volume is this. And you can also see it. Let me see here. All right, in this video, I love it actually. They have a way to measure the displaced liquid. I know it's not very healthy to scroll down. All right, and yeah, this. So they have a container, yeah, and the container has a tube, and they fill the container up to the tube, to the level of the tube. And by immersing the cylinder inside the liquid, any liquid overflow will go out of the cylinder, out of the container, out of the tube into the small beaker. And whatever water you collect here is called the displaced liquid. The volume of the displaced liquid is equal to V immersed. And to be honest, if you take the small beaker and you measure the mass of the water inside and the weight of the water inside, it's going to be equivalent to the Archimedes upthrust. And I believe this is very important. I know it's a bit confusing. Let me say it again. It is important for two reasons. This is history because this is how Archimedes did this in the past. He was using a tube and he was measuring the overflow. Also, Archimedes proved, if you read it, if you read the statement of Archimedes, what is the Archimedes upthrust? The upthrust has a magnitude equivalent to the weight of the liquid displaced. And if you think about it, back to here, isn't it M times G? Isn't rho times V equals to mass? Rho liquid, and this is the displaced volume, you end up with mass. And isn't that M times G? So the Archimedes is equal to the mg, or the weight of the displaced liquid. So if you can collect the displaced liquid in a beaker and go measure the mass and calculate the weight, it's equivalent to Archimedes. We're not gonna do that, but it's good to know. So somebody was asking me about precision. Yes, and the famous Eureka. So the technique is precise. I don't see why not. If you have, why not? Tell me, Jana, I would love to hear you. Why do you think the technique is not precise? If you have water just at the level, probably you can keep on putting water until all of it will go out, and you stop whenever the overflow will stop. And this is where you start dipping. And when you dip the cylinder, let's say half of it, you will have an overflow. And you measure the beaker with the overflow and without the overflow, you can find the mass of the overflow.
But what if some of the water is stuck in the little tube that is supposed to get the water inside the beaker?
All right.
What if not? Yani, what if the volume that was put initially, that is right below the tube, and then when we fill that instrument until it overflows so that it can empty into the small beaker, the volume that empties into the small beaker and that remains in the instrument is different than the initial. Experimentally, I think a lot of things can go wrong.
Yeah. All right. So far you gave me probably 3 sources of errors, if I'm not wrong. And probably we can think together how we can prevent this. By having a very small tube, we have something called capillarity, which means it will never be empty. It will always be full. So if we can increase the tube a bit to prevent capillarity, this is one. 2, what was the other one? So we can fill the container until it overflows and throw the overflow. This could help. Definitely, probably what you're trying to say, Jana, that by simply doing the measurement of volume before and volume after is so simple and quick, and no need to go into a complex procedure. So the procedure being complex, meaning that you have much more sources of errors, and if you want to think of each to prevent it, so whatever you do, it will be less precise. And yes, I agree with you. Yes. So Jana is trying to say probably we can find a method that is less complicated or complex. Complex meaning it has so many steps. All right, she just gave me yeah.
Doctor, بس احنا ما جبنا the F, the force F from weight real minus weight apparent, or not yet?
Yeah, Lambala جبناها. We already have the force sensor and we did the work. So my question
is... So we can apply the formula and get the V immersed, right?
That's method number 2. So Kausar is saying we have F, we have density, we have G, we can calculate Vm. Why not? You are alone in the lab is locked, and the question is find Vm. But how would you find the density of the liquid?
We don't know the liquid that we are using.
It's tap water.
We don't have it, and usually it's not a fixed for every liquid.
How dirty is tap water? I have no idea. Google cannot tell you what's tap water at LAU Jbel campus. You know, it could be dirty and probably.
This is another source of error, and we are assuming, it's
yes, that's
the density
true. That's true. However, your idea holds true. You can still calculate. You can assume that the density of tap water is like regular distilled water, and you can say 1,000 kilogram per meter cubed. And you can say with some sources of errors, I'm going to accept this. Okay, legit. I accept your method. Any other method to measure? Okay, so Romy wants to use a graduated cylinder, and I assume, Romy, you want to measure the volume before immersing, the volume after immersing, and find the difference, right? I think we already discussed that. So probably, let me say, method number one, yes, Romy. Method number one is graduated cylinder. Method number two is the overflow, which is, I believe, the same idea done differently. Method number three, calculate V immersed from the formula. Method number four, you are alone in the lab is locked, you have a cylinder. The question is, find the volume of the cylinder. What do? Easy. Hint, I give you a ruler. How do you measure the volume of a cylinder if I give you a ruler? What is VCI equals VM? V cylinder minus V above water. All right, yeah. So V cylinder, V above water. Okay, but how do you find V cylinder to start with and V above water? Area of each side of the object, you're close. Yeah, area, you're talking about the area of the side. What else? We measure the height, Carl, yes. Add them up, add all the areas. Area times height, thank you, Romy. To find the volume of a cylinder, we can imagine the cylinder to be DVDs on top of each other. And by finding the area of one DVD times the height, that's the volume, right? So, and yes, we can find the height of the immersed part only. How? By simply, I can increase the height of the platform 1 meter up, which means my cylinder, 1 meter, I wanted to say 1 centimeter up, which means my cylinder is dipped in the water 1 centimeter only. I will definitely start with the cylinder just touching the water on the surface, like grazing the surface of the water, knowing the height or the depth of the cylinder, knowing with a regular ruler the diameter of the base, I can find the volume. Now you tell me, Romy, what is the area of the base? So volume is area of the base times height. How do you find the area of the base?
The area of the circle.
Of a disk, which is?
Yes. Pi r squared.
Yes. So pi r squared, which means with a regular ruler, I can measure the diameter. By the way, my dear friends, we had a very similar question in the lab. And somebody from section 1, because they already did buoyant force like 2 weeks ago, told me, like, I realized you will not see it. When the diameter is measured, let's say the diameter it was 2.50 centimeters. I'm thinking sig figs in here. And I'm using a regular ruler. However, in the lab I did, in the video, I would be using a vernier caliper, which is more precise, but let's say a regular ruler. Okay, a regular ruler. Isn't that the error? Correct me if I'm wrong. If I need to find the radius, what do? Wasn't that question in the midterm yesterday? How did you do that? Yeah, how do you find the radius? You simply divide the diameter by 2.
Personally, I divided by 2, but I didn't divide the error by 2 لأنه it's the same ruler. ما اعتبرت إنه we're using it twice, so the error should be divided by 2.
The error should be divided by 2 because the radius is diameter over 2, and this is a function. So you do the derivative, which is 1 over 2 times alpha diameter. which means the error on the radius is gonna be less. And remember, the radius was not measured. It was calculated using d over 2. So you cannot say, I think Kausar was talking, I don't know who. You cannot say, I'm measuring r using the same ruler. No, I'm not measuring r. I'm calculating r. And yes, I'm going to do propagation of error. Okay? I was expecting this to be easy for you, but probably because it's too easy, sometimes you don't see it. You divide the diameter by 2 and the error by 2. Okay, but then you have to round the error because it's gonna be too significant figure. Probably the rounding was wrong, I don't know. What I wanted to say, one more thing. Think about it, which is more precise, to measure the radius or measure the diameter? I think if you measure the whole diameter and divide by 2, it's more precise. I mean, by definition, you know. And if you try to measure the radius, which is smaller, and you're not sure where the center is, it has to have a lot of sources of error. So it makes so much sense to measure the diameter and divide by 2 and not measure the radius itself. Okay, and that's why we actually measure the diameter. So you know instinctively that this procedure is more precise, but you don't know how to write it mathematically. You said it's the same error. No, it's a smaller error. Anyway, I'm happy to discuss this. All right, now I've been talking about so many things and you will end up being a bit confused. Let me try to write the Archimedes upthrust again. I'm practically done. It's dl times g. Instead of Vm, I'm going to write pi r squared times h. And here I need to remind you, h is not the height, really, it's the depth. This is h. Okay, I would love to call it depth, but I don't want you to think it's density. So I'm going to increase the depth again, 0, 5, 10, 15, and so on. So this one is going to be increasing. Obviously, F is going to increase as well. You will not see it directly because you will see the apparent weight. So the apparent weight is going to decrease, 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 decrease. You will feel lighter as you sink more inside the liquid. You not sink, but like you're being dipped more inside the liquid. So and you know the density of the liquid is not going to change, constant. G is not going to change. Pi is constant. The radius is constant. So you tell me, what am I supposed to plot in here to get the linear relationship? What do I plot to get? Yes. Thank you, Kausar and Roy. So F versus H would give me a straight line. Now another question, what does the slope represent? The slope of the line, linear regression. So I'm plotting, yes. So d, g, pi, r squared is gonna be the slope. Now that I know the slope, Kausar, I can find the density of my tap water and check how dirty the water is at LAU. Not really dirty, but it has a lot of minerals, you know? And yeah, and probably, and by the way, I can find the slope and the error on the slope, deduce the density and the error on the density, which means I can tell how precise my experiment is as well and how accurate the assumption of density of water to be 1000 kilogram per meter cubed. Remember, the beakers are dirty because definitely I'm gonna do the experiment again with a lot of salt because I want to see salty water, how does it affect the Archimedes upthrust, which means when you come to the lab, probably a class was there before you and probably those students did not wash the beakers very well and probably the beakers are still a bit salty. And I know you will wash them before the experiment because you want you to be very precise, but what if the beakers are not super clean? What if tap water is not clean in terms of minerals? I'm not talking cleanliness, I'm not talking dirt, but basically minerals. It's not distilled water. Also, what about the temperature? Some of the students would use cold, super cold water and super hot water, probably not room temperature because you know the containers of water at LAU, they're huge and probably water from tap water is colder than room temperature because of the night before, I don't know. So probably this would affect the density in a way. But however, I know that the temperature has a very small effect, but yet it's gonna affect the density. So keep that in mind. Now, Probably my final question is, if I add a lot of salt to my water, like a lot, I'm talking above 200 grams, and I stir for about 2 minutes, because this is what students used to do back in the past pre-COVID. Question is, how do you believe the slope is gonna change, or the line is gonna change when you add a lot of salt? It's gonna remain linear, I suppose. We do the experiment again with a different liquid called salty water. How do you believe the graph is gonna change? Slope is gonna become bigger, yes, because salt and water has a bigger density. Bigger density means bigger slope, so it's gonna become bigger. However, don't be upset. The difference is so tiny that a lot of students see no effect. That's why we ask them to add more salt, and we'll end up buying a lot of salt and throwing a lot of salt, like bags and bags for every bench, just to see a tiny change in the slope. I think the problem is the cylinder is so small. So you need a lot of salt for you to see a big effect on the Archimedes. I think so. All right. Anyway, so now wrap up. You change the depth. You find the apparent weight. You create an extra column to write the Archimedes upthrust, because it's not going to be given to you. You will be given the Archimedes. And then you will plot F versus depth. You can call it high, H. And you find the slope and the error on the slope. Repeat for liquid 2. These are the measurements given to you. You are given the diameter of the disk, regular ruler, so you know the uncertainty. A G will not be given to you, but you can use 9.81 plus or minus 0.1. I know this is an assumption. It's only for you to practice doing propagation of error, because I have no means to measure the gravitational field strength directly. Probably I can do it in a separate experiment one day, propagation of error to find G, and give you exactly, not really exactly, depending on the precision of the experiment, definitely. So you can use those to answer some questions. I closed your manual. It was open a few hours ago, but I have it quick in here. Let me show you what to expect, and you're gonna be happy to see it's very short. I know you have the error on the slope, but that's it. It's not like you have so many other questions. Let me jump to Archimedes buoyancy lab report. Okay. Question to answer before you do the experiment. Data table will be full for you. How do you measure the buoyant force? Just explain if you use the force sensor directly, or you find the apparent weight first, or so on. Then they ask you to plot to find the slope and the error on it. This should not take your time. And please use Excel. If we cannot use it in the midterm, we can use it a lot in the lab reports. Deduce the density with the error on it. And probably they want you to repeat for salty water, discuss precision and accuracy, compare densities, and that's it. So this can take you up to 20 minutes, not more, you see? Now for the videos, I will provide you with 2 videos. One video will be the PASCO video. This is a general video given by PASCO. This will not follow exactly our experiment, but it has 2 experiments. I think they're gonna use, I will try to scroll through it. However, I know.
AJ, what is this?
All right. I know for a fact that scrolling through a YouTube video may not be smart. So let me tell you, they have a force sensor, they have a black cylinder, and they have a container. They can measure the force sensor and the overflow. In our case, we're not doing that. In our case, we're using the force sensor to find F, and we're measuring the depth, okay? But it's nice to see how they do it, the precautions, probably discussing the source of errors, and so on, you know. I gave this video to my students back in the spring of 2020 because it was impossible to go to campus and record a session for them. It was the beginning of the big lockdown, at the beginning of the corona. So we had to give them this. But eventually, Dr. Samar managed to do the experiment herself. And I thought probably you want to see it because it will show you the equipment we've been using. So basically, okay, let me show you a different picture. Okay, she's explaining a bit calibration. And okay, so this is the platform. You see the platform, I can raise it up and down. This is this the stand. And what you see here, Data Studio will give you an actual value. So it's a digital measuring tool, no graphs, no tables, only the value of what the force sensor is measuring. That's it. And again, the force sensor is gonna be measuring the apparent weight. And you continue, probably I can show you how she's dipping. Here she's still explaining a bit. Don't be confused, don't use her measurements. They will give you probably the same results, but I'm scared the measurements are not complete. So she's attaching a wire and the thing. I don't think I can scroll through. I just need to show you the value. All right, she got negative values because she calibrated her force sensor in such a way that a pull force is negative, which is okay. Negative is for direction. You can simply take the absolute value, which is the magnitude of the force. Yes, some students I had in the past had a very interesting idea. They connected or attached the hanging cylinder on the force sensor and then they zeroed the force sensor, which means they zeroed the weight. So anything extra you measure will be the Archimedes force and they don't need to do real weight minus apparent weight. You see? Because they already minus the real weight by doing the zeroing with the real weight on. I'm not gonna do this because I want you to be aware of what we are measuring, okay? Since you have no chance to go to the campus and to see it on the bench, I want to do it step by step. Measure the real weight, measure the apparent weight, the difference is Archimedes. Kausar is asking, number 6, do we have a theoretical density comparing it to an experimental? For the real, for the tap water, we're gonna use 1000 kilogram meter cube to be our reference, which I believe is not very accurate. But we're gonna use it as a reference and compare our measurements to it, okay? For salty water, we don't know because it depends on how much salt you add, but we know for a fact that it has to increase. So some benches will have 1,200, some benches will have 1,100. It has to be greater than 1,000 SI unit for salt and water, you see, depending on how much salt you put. And since I have a small beaker and a small quantity of water, probably even if I put a lot of salt, like only a small fraction is gonna get dissolved, you know? So yeah, that's my limit. It's like I cannot increase the density a lot. A lot of students gave me the idea to use sugar. Sugar will give you a greater density. I never had the chance to try it. We have some sugar in the lab. We wanted to use them. To be honest, I was disgusted. I have issues with sugar because when you have salt all over the lab, all over the benches, you feel less disgusted. But when you have sugar all over the benches, all over your books, it's really messy, you know. Yeah, I'm not a chemist, you know, so I have issues with liquids everywhere. It's a physics lab, so I'm not used to this. I never tried sugar yet, but probably we can try it soon and see if it's gonna increase the density a lot. We can try oil, we can try alcohol. You know, oil, it has a very low density, alcohol as well. But how about you do the cleaning after the oil and the alcohol is easy. Maybe not so easy to provide because we used to buy a lot of stuff every single week. I used to go to the Diken next to LAU to buy salt because sometimes I'm out of salt and I need like 10 kilos for every session because we use, yeah. So imagine us using oil. Yeah, I feel bad because we're throwing a lot of salt, but it's also good to show you. This is also good how the slope is gonna increase a bit. Yes. All right, I'm gonna stop recording, but we can stay to discuss